test. So the class average was actually a 60, and I added 5 points to everyone's test as just a flat curve for the class. So after I added the 5-point curve and counted number 9 as bonus, all right, class average was 65. Standard deviation was 19 points, which is about on par for this class. You know, the spread of the grades was pretty big. High score was 100 after the curve, and the lowest, I just don't remember what the lowest was. I don't think anyone, I don't want to say this, but I don't think anyone was in the 30s. I don't know. I believe that there were 3 A's, 3 B's, something like that. 3 A's, 3 B's, a lot of C's, lots of D's, many F's too. So I attached to your test a piece of paper. This piece of paper is very important. All right? It should have your name, then it should have a number. That's your grade in the class so far. That's taking into account your quizzes. And I've dropped your lowest quiz. That quiz grade is not going to change because we're not going to have any time in class to really do any more quizzes. We're too far behind at this point. So unless I do a take-home quiz or something like that, that grade shouldn't fluctuate much. It shouldn't go down, all right, hopefully. And then the next 3 numbers are what you need on the final exam to achieve that grade overall in the class. So if it's grayed out, that means that that letter grade is not possible unless you score over 100 on the test, which maybe it could happen if there's a bonus on the test. So for example, if you have something like 101, 87, and 61, then of course an A is very, very improbable. But to get a B in the class, you'll have to get an 87 on the final. And to pass the class, you'll need a 61. So the students that I think are in danger that I'd be concerned about, of course, if this is over 100, that's a major concern. But if this is something like, I don't know, 85, yes, it's possible for you to pass the class. But if you're in this category, most likely every exam you've taken has been below 85, which means that that final has to be your best test of the semester. And that is where things can get a little bit dangerous, right? Because you're trying to do something you haven't been able to do yet. That's where we stand, okay? That's the numbers, that's the mathematical where you are, okay? If you're concerned about your grade, please talk to me after class. Unfortunately, I mean, it is after the drop date. That was one of the bad things about pushing that test till last class, is that it pushed us past the drop date. So you had to kind of make an educated guess on how you thought you might do and risk the possibility that you're stuck with where you are, all right? Yes? I'm only saying this because we have 25 students in this class still. We started with 26. We have 25, but there's about 8 people, 9 people that are in like danger zone right now. And so because of that, you know, how do I say this? Not sure what to say. I mean, it is what it is. I mean, there's nothing that can be done at this point except you come in and do well on the final. I mean, that's what can happen. That's what has to happen. So, all right, we move on. We have to proceed. So please get with me if you're concerned about your grade. After class, I'll be here for an hour after class. But we're going to move on to 8.4. And we had started this already last class. Or, yeah, the last time we met, but I said it wouldn't be on the test. And we had started talking about alternating series. So alternating series, well, this is actually called other convergence tests. And just one more piece of advice to you. All right, although I don't think I've given you any advice, have I? So a piece of advice for you. I have a Cal 2 student right now, not in this class. They're actually taking this class online. They took me for Cal 2 last semester, and they got a D in the class. Barely got a D. And they're retaking it now. They're doing it online. They're watching all these videos. They're doing all the homework that I'm assigning out of the book. They're watching all the my solutions. They have requested to take every test that you take. They have taken themselves just to do it. And right now, if they were in this class, they would be an A student. So my point is this. If you are struggling in this class and you are going to be a student who winds up with a D, that's not the end of the road for you. I mean, like, you just have to come back and reapply yourself and see this material one more time. I mean, sometimes that's just what it takes for this class. You have to see it twice. I mean, now, if you do have to take the class again, you will have seen series. You will understand the idea of integration by parts. Everything will be in there. It's just a matter of fine-tuning it now, where you don't make the mistakes, where you come into the test and it's not like, oh crap, I don't have enough time. Because if time is an issue, that means you don't know it well enough. That's what it means. It doesn't mean that you don't know. It's just that you don't know it, you're not strong enough with it yet, where you can produce the answers in the amount of time that you have. So, I just want everyone to keep their head up. It's okay to not succeed in a class, especially Cal 2. It's the hardest calculus class that you will take. Not the hardest class you'll take, but the hardest calculus class you'll take. So, all right. Other convergence tests. So we talked about an alternating series. And an alternating series is any series that just changes signs. All right, so it's going to be like plus, instead of saying this plus this plus this plus this forever, it's going to be maybe this minus this plus this minus this plus this. So we keep getting switching. And so it's going to be some sort of summation, and it's going to go from 1 to infinity. We're going to have something in there to account for the switching of the signs. So that means we're going to have a -1 in here. And then it's going to be raised to either n or possibly, what, n plus 1? And you could actually have some other things, n minus 1 or n plus 3. But no matter what, it's going to be n or n plus 1 or some variation of it to create either your first term being positive or your first term being negative. Which one of these creates a first term being positive? n plus 1, negative would be the n, right? Okay, and then attached to this, we have a sequence defined by n, and we're going to call it b sub n. We're not going to call it a sub n. Normally, we would write this, wouldn't we? Something like that. And a sub n was this sequence. Now what we're doing is we're calling the part that's been peeled off the -1 b sub n. The whole thing together is a sub n. All right? So do you see how the b sub n is like isolating it from the switching part? Yes? Okay, that's an alternating series. And what we're going to look at now is what's called the alternating series test, which is a test we use to determine whether or not an alternating series converges or diverges. You can only use this test on an alternating series. It will not work for something that doesn't alternate. All right? So understand what it looks like? Okay, so let's look at the test. Whoa. So the alternating series test which can be a pain to write over and over and over, so I'll just say AST from here on out, goes as follows. Given an alternating series right? This power up here can be either one, right? Doesn't matter. Either n or n plus 1. Times some sequence. So if we're given a series that alternates, then if we have two conditions. If first, b sub n is greater than b sub n plus 1, eventually, what does that mean? B B sub n is bigger than B sub n plus 1?
Decreasing.
It's decreasing. So if this part, right, not the part with the negative, but if the part separated, if that thing is a decreasing sequence, right, first, and secondly, the sequence converges to 0, then the series converges. I'm out of room. So then the alternating series converges. This is a very nice test because it says if we have an alternating series, we only have to check two things: that the sequence decreases and that the limit of the sequence, there it is, goes to 0. Now remember, this limit n goes to 0 of a sub n, when that equaled 0, right, that was called the nth term test, wasn't it? When it wasn't an alternating series? If we took the limit of what was in here and it went to 0, right, that was the nth term test, and if it went to 0, it told us nothing, right? But with the alternating series test, this actually tells us something. If it goes to 0 and it's decreasing, guaranteed the whole thing converges. All right, so let's see an example. If you look back at the video I did last class, I believe I did this example, but it's been so long. 1 minus a half plus a third minus a fourth plus a fifth minus a sixth plus dot, 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 dot. Does this converge or diverge? Well, let's first write out the sigma form of this. So sum n equals 1 to infinity. Let's make it alternate, right? And let's start with a negative. With a positive, right? So how about we use -1 to the n plus 1? Okay, that'll create the alternating part. And then let's look at each of those fractions. They're all 1 over something, right? So I can say times 1 over, and then what do I want to start with? N, right? N is 1, and I get 1, then 1/2, then 1/3, and then 4th, 5th, 6th, and then it keeps switching signs every time, right? So that should work. All right, so now that we realize this is an alternating series, I focus my attention on this piece, which is B sub n, right? That's the piece that's detached from the negative switching part. And now I just need to show those two things. So first of all, I want to show that this is a decreasing sequence, right? I want to show that. It's going to be pretty easy to show. 1 over n is B sub n, isn't it? 1 over what is B sub n plus 1? 1 over n plus 1, and then you can do the thing that we've done several times now, right? And this turns into n plus 1 greater than n. Subtract n from both sides. 1 is greater than 0. Do you all follow that? That's true? Since that's true, we've met the first condition for this to converge. The second condition is we want to show that the limit as n goes to infinity of B sub n equals 0, right? If we can show that, we're good. But I think that is pretty clean, right? That B sub n is 1 over n. That obviously goes to 0. Check. We're done. That's it. Both of these are true. Therefore, that series converges. Yes? Any questions? That series looked a lot like what series? Harmonic, right? Harmonic looks like what? 1 plus a half plus a third plus a fourth, right? And if I asked you if that one converged, you would tell me what? You'd say diverge, right? You'd say that this diverges? Because it's harmonic. So just by putting those minuses in there, it actually made it converge, right? By making it alternating instead of this. All right, let's take another series here. How about sum n equals 1 to infinity, negative 1 to the n times 3n over 4n minus 1. The thing that tells you it's alternating is pretty obvious, isn't it? I mean, these alternating series, they can't hide from you, can they? A little negative 1 to the n part really kind of reveals itself. So you may be thinking alternating series test here, right? Yes? So what's b sub n? 3n over 4n minus 1. That's our b sub n, isn't it? Anybody notice anything about b sub n? Just right off the bat. It would be infinity over infinity. So you would do L'Hopital's rule on that, and you would get what? 3/4. And that doesn't go to 0, does it? So without really writing anything down right now, I'm recognizing that, right? That I know that's not going to go to 0. So there's no way I can use the alternating series test here, because that's not going to go to 0. So what I'm going to do is I'm going to go to the nth term test, which is the first test we learned. And I'm just going to look at the b sub n for now, just this piece. Limit n goes to infinity of 3n over 4n minus 1. And I know that that goes to 3/4, right? L'Hopital, derivative top and bottom one time, you get 3 over 4. So what happens to this series? What's happening in here? This thing, is it going to 0? No, it's actually getting closer and closer to 3/4, but it keeps flipping back and forth on the sign, doesn't it? And didn't the nth term tell us that if this is not 0, it diverges? Yes? And this is definitely not 0. Especially if I come in here and do plus or minus. No matter what this is, it's not going to 0. Understand? So with that, I just say it diverges. So diverges. All right, now this one's going to be more interesting. Series summation negative 1 to the n times n over the square root of n cubed plus 2. Now let me ask you something. Can I do a comparison test? What were the conditions for the comparison test? If I was going to compare it to something. They have to be positive. Okay, that was the condition. If you look back on your sheet, the main condition before we could even use a comparison test is that the terms of the series had to be positive terms. If they're switching between positive and negative, you cannot use the comparison. So that, again, it locks us into really only one thing right now, right? Which is the alternating series test. Now, a quick check of things. Just looking at the b sub n, does that look like it's going to do what the last one did? If I let n go to infinity, infinity over infinity, I might have to do some L'Hopital there. It's not as obvious as the last one, right? The last one was 3/4, and we kind of knew. So I might have to do some work there. So let me at least try for the alternating series test here. First thing I need to show b sub n is greater than b sub n plus 1. Oh yeah, and this is my b sub n, right? The part circled in red. Let's get an appreciation for just how ugly the next line is going to be, all right? This right here. I'll do it over here so you can see it. It's b sub n, which is n over square root n cubed plus 2. Needs to be greater than, what, n plus 1 over square root of n plus 1 cubed plus 2. Right? That does not look like something I feel like messing with. I mean, we could, but the thing is, you can't just simply look at that and say, yeah, check, right? If you do that, you're flipping a coin, okay? Because you might say to me, well, wait a minute. If the bottom of this one is bigger than the bottom of this one, then this fraction has to be smaller than this one, right? Which it is, right? This bottom's bigger than this one. But the top got bigger also. Right? So if the top got bigger, the fraction got bigger. So you cannot guarantee me right now that this side's smaller than that side. Now, I would totally agree with that logic if you had that, because then this bottom is bigger than this, right? And these are the same, so yes, this has to be smaller. But with the plus 1, it's a bit of an issue. So since I don't want to mess with that, I'm going to start thinking back to how it is that what are other ways I can show that something is decreasing? Derivative, right? This is what we did when we used the integral test. Remember that? One of the things we had to show for the integral test is that our sequence decreased or our function decreased. So if I were to take my sequence, b sub n, and convert it into a function of x, take its derivative, all I'd have to convince you of is that that derivative was negative, right? If it was negative, then it would be decreasing. Maybe it's easier for me to do that. So I don't want to do that. I'm going to let f of x be my sequence, my b sub n, but I'm replacing all my n's with x's. Now, when we did L'Hopital's rule on the test, I said you didn't have to do that, right? Switch it over to x. But this, you do need to do this, because you are actually going to do a quotient rule on this and take a real derivative. It's not L'Hopital here, right? This is like Cal 1 derivative. You ready for this derivative? Everyone see that it's that sequence written as a function of x? Okay, so let me, I want to show now, right? What is it that I want to show? That the b sub n is decreasing, right? Which means I need to show that this is decreasing, which means I need to show the derivative is negative, right? So I want to show everyone right now that the derivative is less than 0. If I can convince you of that, will you be okay with this? Yes? All right, so let me take the derivative. And for the derivative, I will use the quotient rule. Remember the quotient rule? So derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. Well, derivative of the top is pretty easy, right? 1 times the bottom, that's pretty easy. Square root of x cubed plus 2. Minus, now here's where things start to get kind of ugly. We need to take derivative of the bottom. And the derivative of the square root of something, yeah, so the derivative of square root of something is 1 over 2 times the square root of that something. Yeah, and then chain rule. So times, now the derivative of what's inside of it, which would be 3x squared. And then finishing off the quotient rule times the top, which would be x. But it's all of that over what? The bottom squared. Well, that's nice because it gets rid of the square root, doesn't it? Now the question is that a positive or a negative number? Yes, it is, right? Okay. So let me try and clean it up a little bit. Don't know how fast I can do this. I'll go a little slow. X cubed plus 2. How about minus 3x cubed over 2 square roots of x cubed plus 2 over x cubed plus 2. All I did was just kind of put things together over here, right? I don't know if this is negative yet, okay, because, I mean, I know the bottom is positive, don't I? Remember, I'm only going to be plugging in x values that are what? Positive, right? Because remember, my n values will always be 1 or 2 or 3. So I know that if I plug in a positive x here, right, in fact, any x greater than or equal to 1, that this will definitely be positive, right? The problem I'm having is that this right here is positive, and this right here, what is all this? The whole thing. Positive number cubed, this is positive. This whole thing is positive, isn't it? But if I tell you I have a positive number minus a positive number, can you tell me it's negative? You can't, right? A positive minus a positive, you don't know. So I have to go a little further with my algebra here. So how about we get a common denominator between these two right here? So we get, let's see, I'm inserting right here a 1. And then I'm going to get my common denominator, which will be 2 root x cubed plus 2. I'm going to insert it there, and I'm going to insert it on the top here. Yeah? And so when I put the top together here, the roots come together and they go away. And I have a 2 out front. So I'm going to have 2 sitting in front of the root, the radicand, which is the part that was underneath. And then over here, minus, and what? The 3x cubed, and then all of that over the common denominator. And then all of that over x cubed plus 2. Y'all understand what I did there? Now, I know that this is positive and this is positive, right? That's positive number, that's positive number. Just have to resolve what's up there. So let me distribute through. I get 2x cubed plus 4 minus 3x cubed over a positive number over a positive number, yes? As long as x is positive, these two are positive. And that numerator becomes 4 minus x cubed, yes? Over a positive number over a positive number. Is that negative or not? Is it negative right away? No. Not right away, right? So my function is not decreasing initially, right? At x is 1, this is a positive up top, which makes it increase. But when x becomes 2, that becomes what, 4 minus 8? Yeah. And now it's negative. And now any x bigger than that, right, this right here will overpower the 4. And so the top will become negative, yes? So this, even though it's not negative all the time, here's what I can say, is that f prime of x is less than 0 when x is greater than 1, or I'll say greater than or equal to 2. Can we agree on that? And remember, I don't have to have it decreasing all the time. I just have to have it decreasing eventually. And that's eventually. Maybe it would have been easier to do it the other way. I doubt it. This, believe it or not, is more efficient, all right? You good? Okay. So now the second thing. We have to show something else. We have to show, for part 2, the limit as n goes to infinity of the b sub n. Right? That goes to 0. I've seen all sorts of different ways to do this. We have infinity over infinity, so you could do L'Hopital, couldn't you? Yes? I don't feel like taking the derivative of the bottom again, though, because that's too ugly. So just tell me whether or not you believe this is true. This is probably the more efficient way to go about it. Is that the same thing? Yeah? All I did was I rewrote n on top as n squared square root, and then I wrote it all as one fraction. Now, why do I like that? Because then I can pass the limit through the root and just do L'Hopital on that part and not have to worry about the chain rule I would have had with L'Hopital on that. You see what I'm saying? So my next thing, I'll write it out even though I just said what I was going to do. I pass the limit through the root, and I just do the limit on this piece inside. So what happens after L'Hopital once on this? You get 2n over limit, n goes to infinity. You got 2n over 3n squared. And one of the n's cancels, right? One of these n's cancels. And so you really just have 2 over 3n, don't you? And you let n go to infinity. And this goes to what? 0. And square root of 0 is 0. So this goes to 0, which works. What's my conclusion? Therefore, the original series converges, right, by the alternating series test. Do you all have any questions about that one? That's a good example of one where the showing of the decreasing was a little bit involved, and where the showing that the limit of the sequence went to 0 could be a little bit nasty if you just go straight to L'Hopital. If you do a little bit of algebra first, it's a little easier. You could have got it with L'Hopital, all right? You could have just straight off, but we'd still be doing it right now, probably. All right. Now, we have some definitions. And we have another test. I believe this is a theorem. If the sum of the absolute value of a series converges, then the series itself converges. This is on your sheet of tests, I believe. I believe it's the last one. Yes, it's the last one on your list. You see it there on your list of tests? It's the very last one. So if the absolute value of a series converges, then the series itself without the absolute value will also converge. Right, so let me show you an example of this. Sum n equals 1 to infinity of -1 to the n over n cubed. Can anybody tell me what kind of series that looks a lot like a p-series, right? With p being what? 3. And what do p-series with p being 3 do? If it's greater than 1, it converges, right? So that looks a lot like it, except for the negative, right? The alternating part. So what this theorem tells us is this. If you take the absolute value of this, so let's take a look at the absolute value of this series. Then that's the same as, what is taking the absolute value of -1 do? It always makes it +1, right? So what this absolute value does is it kills off the alternating part and makes it 1 every single time instead of switching back and forth. So the top becomes a 1 and the bottom becomes n cubed. This series is p series, right? P being 3, greater than 1. Therefore, it converges, right? So look, here's the original series, right? We wanted to know what it does. We took the absolute value of the inside, and that converged, didn't it? What does that mean? This converges. That's what this theorem says. If you're trying to figure out what this is, take the absolute value of it. If the absolute value of it converges, then so does what you were looking at. So in this picture, this piece, this right here is this one, and this right here is that one. Understand?
Is there a name for this test?
I don't,
Which we have to
not as a test. No, I don't think so. I've never heard of the name.
So we don't need to write this converges by that test?
No, no. Well, let me write a definition down, and then that's what we'll say, all right? So we did something like this. What we said was that we said if, it was sequence, if the absolute value of a sequence converged to 0, then so did the sequence. But this is a series now, so it's a little different. So this is a definition now. I'll just put def for definition. If the absolute value, right, of a sequence, this series, taking the absolute value in here, if this converges, we say that the series without the absolute value is absolutely convergent. I've never liked this definition, and I'll explain why. When I hear the word absolutely convergent, I think it always converges. But that's not what they mean by absolutely. What they mean is that if the absolute value, right, converges, then we call it absolutely convergent. Yeah. But the theorem says that if this converges, that one does too, right? Yes? So if that converges, this one also has to converge. So when that happens, we say it's absolutely convergent. So in that last problem that we did, we would just say, it converges and is absolutely convergent. Let me show you something to be careful with, all right? Let's go back to this example right here. 1 minus a half plus a third minus a fourth plus a fifth, dot, 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 right? That was the first example we started with. What did this do? We said it looked like a harmonic, but it alternated, right? What did it do? We just did it. It converged, right? So when we converted it over, this is what we converted it to, right? Yeah? Now let's start over and let's act as if we didn't know how to do it, and let's use what we just did a second ago. Let's take the absolute value of it, right? So what is the absolute value of this inside going to be? So what's it going to do to that -1 right there? Just changes it to a 1, right? So this just turns into 1 over n. But that's what? A harmonic, and that what? Diverges. So were we incorrect when we did it the first way? Look at the theorem carefully. It said if the absolute value of the series what? Converges, then the original one converged, right? It says nothing about if the absolute value of it diverges. If the absolute value of it diverges, you can't use the theorem. All right, so you have to be extremely careful. There's nothing wrong in the math. It's just that this conclusion does not allow us to draw the conclusion of the theorem. Yeah, it's inconclusive at this point. If it failed to to give us anything useful. But we did it by the alternating series test and found it converged. So what you wouldn't want to do is do this, 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 and say, OK, then that diverges, because that would be incorrect. Yes, you could say this one proves convergence. Yes. For only alternating series, though, that would be really the only time that that absolute value would be useful, because it would change your alternating series into something that doesn't. Does it make sense that it would converge? I've always wondered, think about this. If I'm trying to figure out what a sum is, right? That's A1 plus A2 plus A3 plus forever, right? I'm trying to figure out what that is. And let's say that it's alternating, all right? So let's say some of these are negative, like say that one's negative and this one's negative. Then you have like a number, you're taking away a number, adding a number, taking away a number, right? It's switching back and forth. Then if I take the absolute value of this, doesn't it turn each one of those things into a positive number? Doesn't it? And so if this adds up and it converges to a number, does it make sense to you that this would have to? Shouldn't this be less than this? Because isn't this everything this is except there's stuff taken out? Right? Like this A1 was A1 here. These are the same numbers, aren't they? This one you're taking A2 away, and this one you're adding it. So this one's, these two together should be smaller than these two together, right? And so if that all adds up to be a number, the top one should be less, and so if this one converges, so does that one. Not to the same number, but it's convergent. All right, I hope that kind of makes sense. If not, it's OK, just use the theorem. All right, next idea. Some examples here. We're not going to run through these. I just want to talk about them. This series that's the alternating harmonic series, isn't it? That's our alternating harmonic. Is that convergent? Yes. This converges, right? Is it absolutely convergent? No? If you take the absolute value of this, it becomes harmonic, doesn't it? And so the answer here would be no. And that's why I said I don't like the name absolutely convergent. You would think that if this series converges, we could call it absolutely convergent, right? Am I the only one that doesn't like the language there? I have a series that converges, but I can't call it absolutely convergent. But it converges. So why can't I call it absolute? Because when I take the absolute value of the pieces, it doesn't converge. Yes?
I was going to say, because maybe they're using absolutely as in like...
That's right. You have to look at this word as the absolute value as opposed to absolute like total convergence. It's not like the greatest type of convergence you can have. It's just absolute values converge. I don't know. You see what I'm saying, the difference? Like I think absolutely it's like the top type of convergence you could possibly have. But it's not. OK, how about this one? Is that one convergent? That converges, yes. Is it absolutely convergent? Yes. So I just wanted to contrast two different series. Here's a convergent series that's not absolutely convergent. Here's a convergent series that is absolutely convergent. So we have one final definition. This is the definition. It says this, if A sub n converges, but the absolute values diverge, we call the original series conditionally convergent. That's the term we use for it. Can somebody give me an example of a conditionally convergent series?
The second last one.
The what? The alternating harmonic one that I just showed you, right? That's what this definition is talking about. As an example of this one right here is conditionally convergent, right? This series by itself converges. The absolute value of it diverges. It's conditionally convergent. All right. Now, time for a new test. Three stars next to this test. Ratio test. I'll even put 3 stars at the end of it. We're going to use this a lot in the next, but we only going to meet 3 more days after today. We have next Tuesday, Thursday's Thanksgiving, so we're off. Then the following week we have Tuesday and Thursday, and that's it. I know, it's all coming to an end. And we've only covered 50% of the material in the course, so we still have half. No, I'm just kidding. Okay, so here's the ratio test. It's on your sheet, okay? This is extremely powerful test, all right?
Is it the last one?
I'm sorry?
Is it the last
It's not the last one. We still have the root test. But this one is used far more than the root test is. The ratio test says this, all right? We are given a sequence, and it does not have to be positive. It can be alternating, all right? This can be an alternating series. Did I say sequence? Okay. We are given a series. It can be an alternating series. Then ratio test says this. If, well, I'm not going to say if. I'm going to say this. I'm going to say calculate the following. The limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Whatever this answer is, if it's even possible to compute it, let's call it L for a limit, right? Because that's a limit. We calculate this thing that we will call L. That's the ratio test. If L is less than 1, we have convergence of this series. Since this is all on your sheet, there's no sense in me writing it down exactly that way. If L is greater than 1, we have divergence. What if L is 1? Test fails. That's not going to happen often, but we do need to keep in mind that if the ratio test yields 1, we got to go to something else. Are there any comments on the sheet that I gave you? You know, they're on the far right side, there's some comments. So what does it say about the ratio test over there on the side?
Inconclusive if L equals 1.
Okay.
For a sub n involves factorials or powers.
Okay, that's the part I wanted to hear. This fails if L is 1, it fails. But more importantly, this is a very useful test when you have powers of n and factorials. I don't know if you've noticed this, but I've really avoided factorials, haven't I? I mean, I really have. I mean, on the test I gave you a sequence with a factorial, but I have been very careful not to put any series up here with a factorial. And the reason is because they're difficult to deal with. all right? Especially if we ever had to do a derivative, you can't do it for a factorial. So let's see this thing in action. Do you care why this works now? You do? Now, I'll try real quick. This is the ratio we're looking at, right? We're looking at this ratio. So remember, you have a sequence of dots, don't you? You have a sequence of dots, and you're adding those up. What we're looking at is you're taking the n plus 1 one. So if I look at this, here's the n plus 1 piece of the numbers, right? This is the one right before it. That's the nth one. What we're saying is if you take whatever number this is, so however high that number is, however high that dot is, and you divide it by however high that number is, that is a ratio, right? If that ratio is less than 1, then what's happening is that as you go out, these are actually staying close enough to each other. Like the ratio of these distances between the next one, the next one, the next one, is small enough that it can't possibly blow up and become divergent. I don't know if that makes any sense. Whereas if it's bigger than 1, then what's happening is when you take this ratio, the next one is far enough above that the next one also has to be far above that. And what happens, the spread of them is big enough that it will diverge. If the ratio is 1, you don't know what's going to happen. So I hope that kind of makes a little sense. That's in no way a proof. It's just more of kind of a logical thought process. All right, this is a good one. Sum n equals 1 to infinity of n factorial over n to the n. Now, let's try and think about how we would do this without the ratio test. It's not an alternating series, so you wouldn't even think that, right? No alternating series test. So that means we have like, what, integral test, comparison test. Right, is it a geometric series?
Can we take integral to factorial?
Yeah, we don't know how to integrate factorial, do we?
Can we?
No.
I meant like at all.
The factorial later on in math becomes the gamma function, and the gamma function can be integrated. In other words, the factorial, as far as we know it, is only defined like 1 factorial, well, 0 factorial, 1 factorial, 2 factorial, 3 factorial. But the gamma function is defined like at 1/2 and everything in between, so it becomes a continuous function, and yes, you could integrate it, but not the factorial that we know here. Does that answer you enough? Okay. Comparison, geometric. Now, so ratio. Let's try it. We have never used ratio. Let's just see the beauty of ratio here, all right? Not ration, ratio. All right, the ratio test. So I'm going to compute this thing called L, right? And it's going to be a limit. Don't forget to write your limit. I actually did not give full credit to people who left limit off on this test. Limit, I'm going to do an absolute value. I've got to do on the top a sub n plus 1, right? Now, a sub n is this, right? That's a sub n. So I need to plug n plus 1 in. So it's n plus 1 factorial over n plus 1 to the n plus 1, yeah? That's what happens when I plug in n plus 1 for n. I'm dividing that now by what? A sub n, which is n factorial over n to the n. That look like a mess to you? You have a fraction divided by a fraction. So that's the same as multiplication of the reciprocal. So wouldn't this one flip like this? Okay. I do agree that when you look at this, you're thinking, I do not want to take this limit. It is not looking very nice, right? But because of the fact we have exponents and factorials, things are going to be really, really nice here. What's the one on top there? N to the n is up here, and on the bottom, n factorial. You okay with that? Flip. Let's just try it real quick. N goes to infinity. Infinity? Infinity to the infinity? Over infinity plus 1 to the infinity plus 1 times infinity, which is infinity over infinity, right? Can't use L'Hopital, because can't take derivative of a factorial. But there are some things we do know about factorials. And there are some things that we know about exponents. So see if you believe this, agree with this. This is just going to be algebra at this point. Limit. What can I do with that n plus 1 factorial? Separate it out as a what? N plus 1 times n factorial, right? On the bottom, this n plus 1 to the n plus 1, couldn't I do n plus 1 to the n times n plus 1? Right? We did that a lot with geometric series where we had like a plus 1 and we really split it apart, right? We did that? Okay, and then up here, n to the n, I'm just going to leave n to the n. And on the bottom here, n factorial, I'm going to leave n factorial. And you see some cancellation we get here? N factorial, n factorial, n plus 1, n plus 1. All you're left with is the limit as n goes to infinity of the absolute value of n to the n over n plus 1 to the n. Now, do I really need the absolute value anymore? I actually never needed it because this was not an alternating series, but I would just get into the habit of keeping it, okay? Trust me. Keep it, keep it, keep it, keep it till the very end. Now, this doesn't seem to have helped me. I still have infinity to the infinity over infinity to the infinity, right? But I can turn this into limit. N goes into infinity. And then that's n over n plus 1 in parentheses to the n. Right? And what happens as n goes to infinity here? What does this go to? Just in here, what does this go to? Infinity over infinity, which would go to what, though? This is, in particular, going to go to what? 1. Right? By L'Hopital's rule, this would go to 1. So this is going to 1, and this is going to infinity. And so what we have is something that looks like this, 1 to the infinity. And so what did we do in Cal 1 and in this class when we had this form? Is this an indeterminate form? Yes. So we did something with this. We did ln on both sides, and that's where we're headed. You ready? Okay.
Can we also say 1 to any number?
Well, the thing is, this is not 1. It's getting close to 1, but it's not 1. Right? I agree with you. 1 to any power is going to be 1. But this number's never 1. It's getting closer, so you can't use that. All right, so what do you want me to do? All right, so what we do, this is again drawing back to like a calculus class. I'm going to rewrite this limit n goes to infinity. I'm going to go ahead and get rid of the absolute value right now because I'm just going to go figure out what this is. And then once I figure out what this is, I'll continue over here, okay? So, Ivana, you said take natural log on both sides? Or no, Kieran said that, right? Natural log on both sides. So you create an equation. You call this limit that you want to find, you call it y. And then you take the natural log on both sides. Natural log y equals limit n goes to infinity. And the whole reason we do that is because on this right side, we'll be able to do what? Pull that power n down in front. This n comes down.